7, Section 5, Modeling the 4% Withdrawal Rule of Thumb. Now, the 4% rule states that if you withdraw 4% from your retirement savings in the first year of your retirement, and then increase the withdrawals for inflation to maintain real consumption, you should safely have enough money to last your life, about 30 years longer. And it assumes you have equal amounts of stock and bond in retirement. Well, let's use it at risk to find out the probability that this is an appropriate withdrawal amount from your retirement portfolio. So what I'm going to assume is your portfolio, just for round numbers to make them visually easier to comprehend. Say you have saved $100,000 for retirement. You're going to withdraw $4,000 today. That portfolio of $100,000 is going to earn 5.5%. Inflation's 2%, so that $4,000 is going to grow by 2% per year. And the portfolio standard deviation is 10%. So I'll go to my spreadsheet. I'm going to start off today, $100,000 minus $4,000. All right, because I want to put the money so I can start living my first day in retirement. Now notice I have a little calculation here. That is the $4,000 times 1 plus inflation to the I, the T power here. So what that says is the first year, it's going to be 4,000 times 1.02 to the 0 power, which is 4,000. However, when I have that for the second year, it's going to be the prior year's balance minus $4,000 times 1.02 to the first. So what that does, it's going to increase my withdrawal from $4,000, increasing it by 2%. That portfolio will then grow at 5.5% plus a random shock, 0 mean, 1 standard deviation, times the standard deviation. I can then copy that formula down. This tells me how much money I expect to have at the end. Now, it's not surprising. My portfolio is earning 5.5%. I'm only withdrawing 4% a year, but then that 4% grows. So what you see is it maintains its value over time. Its nominal value, all right, in real terms, it is getting smaller. However, let's make that an output. I now have 30 inputs, those risk normal 0 ones. I'm going to run a simulation while clicking on this cell. This is going to be an output, add output. And I'm not going to run this right now. I'm just going to show you the results because sometimes when I look at it while recording the video, it shows up on different screens. So let's just show you what happens when you run it. What that shows you is the distribution of this final number. It has an average of 115. I then type in 0 at the top of my histogram, my distribution, and it tells me that 77% of the time this portfolio value is greater than 0. In other words, about 24% of the time it's less than 0. So what I can say is this strategy, withdrawing 4% of your portfolio for 30 years and having that withdrawal grow by inflation, is about 77% confident that that strategy will be solvent. So that's a way of thinking about whether the 4% rule is appropriate. And I guess it is if you're comfortable with a 76 or 77% probability. Now, a couple of last things I want to do before we end this topic. I want to go back to my spreadsheet, and I want to talk about real rates of return, another way of thinking about modeling financial planning spreadsheets. Let's say the real rate of return, 5.5% over 1 plus inflation minus 1, gives me a real return of 343. All right, let me zoom in a little bit. So there's my 5.5% at 2% inflation is a real rate of return of 343. And then I could do a calculation here. How much money will I have in the future, a future value, if I have a real rate of return of 343 for 30 years and a payment of $4,000 and I have $100,000 present value in my portfolio? That tells me that I should have $63,969 in the future. However, this is the real rate of return. So what this is really telling me is the real value of my portfolio in 30 years is $63,969. What this allows me to do is it's telling me that my payments are also real. Since I'm using a real interest rate, this is a real portfolio value at maturity. This is the real value of my portfolio today. That's the same as the present value. However, this $4,000, that's a real payment. In other words, it's modeling as if that $4,000 is growing by inflation by the fact that I use the real interest rate here. And so again, it tells me I'll have $63,969 in real dollars. And then I did a simple calculation. I take the $69,000 and I multiply it times 1.02, the inflation rate, to the 30th power. And that tells me that 63,000 real dollars in 30 years is really 115,871, which is the same value as here. The reason why I'm showing you this is in finance, we often will model financial planning and retirement planning in real dollars. That allows me to think about whether my real consumption has changed or not. So I just want to throw that out. We're going to be using that in the next topic. And the other thing I want to show you is I want to model death. So the last analysis says I retired at age 65 and I have enough money, 77% confident my money will last till I'm age 95. The question is, how likely is it that you'll live longer than 95? Well, I've got a random model of death for you. Come over here to the right a little bit. I've gotten some data from our actuarial science people, and they tell me that if you make it to the age of 65 and you've retired, you have a mean life expectancy of 85 years. All right, so that's a conditional life expectancy. In other words, if you've made it to the age of 65, you are likely to make it to the age of 85 because you haven't died yet, and with a standard deviation of 7 years. So if I take 85 and assume the normal distribution of life, 85 plus risk normal 0.1 times the standard deviation of lifespans. This is now my random walk model of life or death. And if I run this, I make this an output. So I made that cell an output. And I run it, I get this graph. The mean life is 85. If life is normally distributed, my 5% highest, my probability that I live past the age of 95, typing in 95 here, you have about an 8% chance of living past the age of 95 if you've made it to 65. So this gives me an idea of whether or not I have enough money. I'm 77% confident my money will last till age 95, and I'm 7.7% confident I will not live longer than 95. So this finishes topic 7, multi-period portfolio modeling, where we constructed static and stochastic models using just Excel, macro Monte Carlo models in Excel, and using at-risk. We've also explored the 4% withdrawal rule, the rule of 72, your age and stock asset allocation rule, and the 10% savings rule.